You know what's humbling? Realizing that every human drama, every war, every triumph, every heartbreak in all of recorded history happened on a planet that's basically a pixel in a photograph of our galaxy. And our galaxy? Well, according to the latest discoveries, calling the Milky Way a grain of dust in the cosmic ocean might actually be giving it too much credit. It's more like claiming a single atom in a grain of sand is significant when you're standing on a beach that stretches to infinity. But hey, at least we're self-aware atoms, right? The recent findings from the James Webb Space Telescope, the European Space Agency's Gaia mission, and the Dark Energy Spectroscopic Instrument have revealed something that should fundamentally change how we think about our place in the cosmos. The universe isn't just big, it's incomprehensibly, almost insultingly vast. And our Milky Way galaxy, home to hundreds of billions of stars and everything humanity has ever known, is just one speck among potentially 20 trillion galaxies in the observable universe alone. Let's take a journey through scale, time, and cosmic perspective to understand just how breathtakingly tiny and yet how remarkably special our corner of existence really is. The Milky Way, our cosmic address. Before we zoom out to the incomprehensible scales of the universe, let's start with something we can at least pretend to wrap our minds around: our home galaxy. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms winding outward. It's approximately 100,000 light-years across. That's about 587 quadrillion miles, if you want to put it in terms that are still completely meaningless to human intuition. The galaxy contains an estimated 200 to 400 billion stars, each one a sun potentially surrounded by its own system of planets. Our sun, that brilliant yellow star that defines our days and seasons, sits about 26,000 light-years from the galactic center, roughly two-thirds of the way out toward the edge. We're in what's called the Orion Arm, or Orion Spur, a minor spiral arm between two major arms named Perseus and Sagittarius. It's a fairly quiet neighborhood by galactic standards. Not too crowded, not too isolated, just right for a planet to develop complex life without too many catastrophic events. At the heart of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass about 4 million times that of our Sun. This monster lurks at the galactic center, around which all those hundreds of billions of stars orbit. Our Sun completes one orbit around the galaxy, approximately every 225 to 250 million years, a period called a galactic year or cosmic year. Think about that. The last time Earth was in this exact position in its galactic orbit, dinosaurs were just beginning to appear. When we complete this current orbit, humanity will likely be either extinct, evolved beyond recognition, or spreading across the stars. That's how slow and majestic galactic motion is. The velocity of our solar system as it orbits the galactic center is mind-boggling. About 828,000 kilometers per hour, 514,000 miles per hour. At this speed, we could travel from Earth to the Moon in less than half an hour. Yet despite this tremendous velocity, the distances involved are so vast that one complete orbit takes 250 million years. The Milky Way's spiral structure isn't static either. Those beautiful arms we see in photos of similar galaxies aren't fixed structures like the arms of a pinwheel. Instead, they're density waves, regions where stars and gas are temporarily compressed as they move through their orbits. Think of them like traffic jams on a highway. The jam itself doesn't move as fast as the individual cars, but the pattern persists because cars are constantly entering and leaving the congested region. This means that stars, including our Sun, move in and out of spiral arms over the course of their orbits. When our solar system passes through a spiral arm, we're in a region of active star formation, with massive young stars that burn bright and die young, producing supernovae. Some scientists have speculated that passages through spiral arms might correlate with mass extinction events on Earth due to increased radiation from nearby supernovae, though this remains controversial. The galactic disk itself is surprisingly thin relative to its diameter. If you shrunk the Milky Way down to the size of a DVD, the disk would be about as thick as a sheet of paper. Most of the galaxy's stars reside in this disk, orbiting in roughly the same plane. But there's also a spherical halo of older stars and globular clusters, dense balls of hundreds of thousands of ancient stars, that orbit the galactic center in all directions. Recent measurements have revealed that the Milky Way is actually larger than previously thought. The traditional estimate of 100,000 light-years for the galaxy's diameter now seems conservative. When you include the outer reaches of the stellar halo and the dark matter halo that surrounds everything, the Milky Way's influence extends perhaps 200,000 light-years or more from the center. Our galaxy is growing, constantly accreting smaller dwarf galaxies and stripping them of their stars. Recent observations from the Gaia spacecraft, which completed its 11-year survey in January 2025, have revealed that our galaxy is far more dynamic than we thought. It's not a serene spiral sitting peacefully in space. Instead, the Milky Way is warped, wobbling, and rippling like the surface of a disturbed pond. In October 2025, Gaia data revealed a giant wave rippling outward from the galaxy's center, spanning tens of thousands of light-years. Scientists don't yet fully understand what's causing this massive undulation, but it's clear our galaxy is constantly being shaped by gravitational interactions, past collisions with smaller galaxies, and the complex dance of dark matter that permeates everything. The precision of Gaia's measurements is almost unbelievable. For its brightest targets, the spacecraft achieved accuracy to within 24 microarcseconds, roughly equivalent to measuring the diameter of a human hair from 1,000 kilometers away, or spotting a coin on the Moon from Earth. This level of precision allowed Gaia to measure not just where stars are, but how fast they're moving toward or away from us, and how they're moving across the sky. With these measurements, astronomers can rewind or fast-forward the cosmic clock. They can trace stars backward in time to see where they came from, revealing which stars were born together in the same cluster billions of years ago, even though they're now scattered across the galaxy. They can also project forward, showing how the familiar constellations will slowly morph into unrecognizable patterns over hundreds of thousands of years. The Milky Way is also scarred by its violent past. Gaia discovered evidence of multiple galactic collisions, including one with a galaxy nicknamed Gaia Sausage Enceladus about 10 billion years ago. That merger significantly sculpted our galaxy's current form and may have triggered bursts of star formation, possibly even contributing to the conditions that eventually led to our solar system's birth. When Gaia Sausage Enceladus collided with our galaxy, it wasn't a gentle merging. The impact sent shockwaves through the Milky Way's disk, triggering massive waves of star formation and fundamentally altering the orbital patterns of billions of stars. Some of these stars still bear the chemical signatures of their origin in the destroyed galaxy. They have different ratios of elements compared to stars born in the Milky Way, marking them as immigrants from another world. The data also revealed enormous tidal tails, streams of stars stretching across space, torn from smaller galaxies as they're being consumed by the Milky Way. These stellar streams are like fossils, preserving evidence of past collisions and providing clues about the distribution of dark matter. The way these streams are shaped and disrupted tells us about the invisible dark matter halos through which they're passing. One particularly fascinating discovery from Gaia is the identification of hypervelocity stars. Stars moving so fast they'll eventually escape the Milky Way entirely. These cosmic refugees were likely accelerated by close encounters with Sagittarius A star, the supermassive black hole at our galaxy's center, or by supernova explosions in binary star systems. Some of these stars are traveling at more than 1,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in less than 6 minutes. So yes, the Milky Way is vast, ancient, dynamic, and our entire cosmic home. Every star you see with your naked eye on a clear night is part of this galaxy. Every constellation, every nebula visible without a telescope, every pinpoint of light in the night sky that isn't a planet, all Milky Way citizens. And yet, as we're about to discover, our magnificent galaxy is barely a blip in the cosmic expanse. The local neighborhood, barely scratching the surface. Our galaxy doesn't exist in isolation. The Milky Way is part of the local group, a collection of more than 50 galaxies bound together by gravity and occupying a region about 10 million light-years across. The local group's two largest members are the Milky Way and the Andromeda Galaxy, also known as M31, another spiral galaxy roughly 2.5 million light-years away. Andromeda is actually larger than the Milky Way, containing about 1 trillion stars compared to our few hundred billion. The two galaxies are on a collision course, approaching each other at about 110 kilometers per second. In roughly 4 to 5 billion years, they'll merge into a single giant elliptical galaxy that astronomers have playfully nicknamed Milkomeda or Milkdromeda. Don't worry about the collision though. Space is so vast that the likelihood of any two stars actually hitting each other when the galaxies merge is essentially zero. Earth and our Sun will likely survive the merger intact, though our night sky will look dramatically different as Andromeda looms larger and larger over the eons. The collision will be a spectacular but slow-motion cosmic dance lasting billions of years. As the two galaxies approach, their mutual gravity will distort their shapes, pulling out long tidal tails of stars. The first pass might send the galaxies careening past each other, only to be pulled back together by gravity for a second collision. Eventually, after multiple passages, the two will settle into a single, merged system. During the merger, the supermassive black holes at the centers of both galaxies, Sagittarius A* in the Milky Way and the even larger black hole in Andromeda's core, will gradually spiral together. When they finally merge, they'll produce gravitational waves so powerful they could be detected by civilizations halfway across the universe. The merged black hole will have a mass of more than 100 million suns. The local group also includes the Triangulum galaxy, M33, the third largest member with perhaps 40 billion stars, and dozens of smaller dwarf galaxies. Some of these dwarfs orbit the Milky Way as satellites, including the large and small Magellanic Clouds, visible from the southern hemisphere. These irregular dwarf galaxies are being slowly torn apart by the Milky Way's gravity, leaving streams of stars trailing behind them, cosmic breadcrumbs that Gaia has mapped in exquisite detail. The Magellanic Clouds are remarkable objects in their own right. The Large Magellanic Cloud, about 160,000 light-years away, contains the Tarantula Nebula, one of the most active star-forming regions in the local group. If the Tarantula Nebula were as close to us as the Orion Nebula, a mere 1,500 light-years, it would cast shadows on Earth at night. The small Magellanic Cloud, slightly farther away, has a lower metallicity than the Milky Way, fewer heavy elements, suggesting it's more chemically primitive and gives us a glimpse of what galaxies were like in the early universe. Other satellite galaxies of the Milky Way include the Sagittarius dwarf elliptical galaxy, which is currently passing through the Milky Way's disk and being torn apart in the process. In another few 100 million years, it will be completely absorbed, its stars becoming part of the Milky Way. This process of galactic cannibalism is ongoing. The Milky Way has consumed dozens of smaller galaxies over its history, and continues to do so. Recent discoveries have revealed that the local group might contain many more dwarf galaxies than we've detected. These ultra-faint dwarfs contain as few as 1,000 stars and are extraordinarily difficult to find against the background of more distant galaxies. Simulations suggest there could be 100 or more such galaxies orbiting the Milky Way and Andromeda, most still undiscovered. But the local group is itself just a tiny neighbourhood in a much larger structure. The local group is part of the Virgo supercluster, or more precisely, as astronomers discovered in 2014, we're part of an even larger structure called the Laniakea supercluster. Laniakea, Hawaiian for immense heaven, spans 520 million light-years and contains roughly 100,000 galaxies with a total mass of about 100 million billion suns. The Milky Way sits near the outer edge of this supercluster, in what's basically cosmic suburbia. Even Laniakea is just one supercluster among countless others. These superclusters are connected by vast filaments of galaxies forming the cosmic web, a phone-like structure where galaxies trace out threads and sheets surrounding enormous voids of nearly empty space. The largest known structures in the observable universe are galactic walls or sheets. The Sloan Great Wall, discovered in 2003, spans about 1.4 billion light-years. The Hercules Corona Borealis Great Wall, found in 2013, might extend 10 billion light-years, though its exact size remains debated and difficult to measure. These cosmic structures represent the largest patterns in the universe, shaped by the initial density fluctuations from the Big Bang and sculpted over billions of years by gravity and dark matter. They're as large as structures can get while still being gravitationally bound or meaningfully connected. And our Milky Way? It's one tiny dot in one filament of this incomprehensibly large cosmic web. The observable universe, the edge of what we can see. Now let's zoom out to the truly mind-bending scales. The observable universe is everything we can theoretically detect from Earth, the entire cosmic volume from which light has had time to reach us since the Big Bang. This doesn't mean we can see it all clearly, it means light from these distant regions has had time to travel to us. The observable universe has a radius of about 46.5 billion light-years in every direction, giving it a total diameter of approximately 93 billion light-years. Wait, you might be thinking, if the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? Shouldn't light have only travelled 13.8 billion light-years? The answer lies in cosmic expansion. Space itself has been expanding since the Big Bang, carrying galaxies away from each other. A photon emitted from a galaxy shortly after the Big Bang began its journey when that galaxy was much closer to what would become our location. But as the photon travelled toward us for 13.8 billion years, space was continuously expanding, stretching the distance. That galaxy has been carried away by expansion and is now about 46.5 billion light-years away from us, even though the light we're receiving left it 13.8 billion years ago. To understand this better, imagine you're trying to walk forward on a moving walkway that's accelerating backward. Even though you're walking forward at a constant speed, the distance between you and your starting point grows faster than your walking pace because the walkway itself is stretching. The photon is like you walking forward, and the expanding universe is the accelerating walkway. This is why we can observe galaxies receding from us faster than the speed of light, without violating relativity. They're not moving through space faster than light. Space itself is expanding, carrying them along. Nothing can move through space faster than light, but there's no limit to how fast space itself can expand. The most distant objects we can observe are not galaxies, but the cosmic microwave background radiation itself, the afterglow of the Big Bang. This radiation was emitted about 380,000 years after the Big Bang, when the universe cooled enough for the first atoms to form and photons could finally travel freely through space without being immediately scattered by free electrons. The CMB is extraordinarily uniform across the sky, varying in temperature by only about 1 part in 100,000. These tiny variations, measured with exquisite precision by satellites like COBE, WMAP and Planck, represent quantum fluctuations from the very early universe that were stretched to cosmic scales by inflation. These fluctuations became the seeds from which all large-scale structure grew: galaxies, galaxy clusters, superclusters, and the cosmic web itself. The observable universe contains an estimated 2 trillion galaxies, according to some calculations, though recent analyses using data from the Hubble Space Telescope and increasingly the James Webb Space Telescope suggest the number might be even higher, perhaps 6 to 20 trillion galaxies when accounting for the smallest, faintest dwarf galaxies we can't yet directly detect. Let that sink in. 2 trillion galaxies, at minimum. Each galaxy contains anywhere from a few million to several trillion stars. If we estimate conservatively at 100 billion stars per galaxy on average, that's 200 sextillion stars in the observable universe. That's 2 followed by 23 zeros, or in more familiar notation, 200 quadrillion stars. To put this in perspective, there are more stars in the observable universe than grains of sand on all the beaches on Earth. In fact, there are probably more stars than grains of sand in all the deserts and beaches combined. The comparison isn't even close. And each of those stars is a sun, potentially with its own system of planets. Even if only a tiny fraction of stars have planets in the habitable zone, the region where liquid water could exist, we're talking about billions upon billions of potentially habitable worlds. The observable universe also contains roughly 10 to the power of 80 atoms. That's a 1 followed by 80 zeros. This is sometimes called the Eddington number, after astronomer Arthur Eddington, who first estimated it. It's the total number of protons in the observable universe, and thus roughly the total number of hydrogen atoms, since hydrogen is by far the most common element. Recent measurements have also revealed unexpected structures at the largest cosmic scales. The cosmic web of galaxy filaments and voids was predicted by simulations, but observations have shown it's even more pronounced than models suggested. Some voids are so large, hundreds of millions of light-years across, that they contain only a handful of galaxies. Meanwhile, filaments can stretch across 1 billion light-years, containing thousands of galaxies all strung together by gravity. And that's just in the part of the universe we can see. James Webb's revelation: more galaxies than we ever imagined. In April 2025, the James Webb Space Telescope delivered findings that stunned the astronomical community and recalibrated our understanding of cosmic scale yet again. JWST pointed at what seemed to be an empty patch of sky, much like Hubble did with its famous ultra-deep field image in 2004. But Webb's infrared eyes can see through cosmic dust and detect light from the most distant, earliest galaxies. Light that's been stretched into the infrared by 13.8 billion years of cosmic expansion. What Webb found was staggering. In what astronomers are calling the deep infrared mosaic, JWST detected more than 25,000 galaxies in an area of sky roughly the size of a grain of sand held at arm's length. Most of these galaxies were invisible to Hubble and all previous telescopes. Dr. Lena Serrano, an astrophysicist with the European Space Agency, summed it up bluntly. We used to think we had a good handle on how big the universe was. The James Webb just showed us we were barely scratching the surface. Many of these newfound galaxies date from just a few 100 million years after the Big Bang, revealing that galaxy formation began earlier and proceeded more rapidly than theoretical models predicted. The density of galaxies Webb found was significantly higher than expected, suggesting that previous estimates of the total number of galaxies in the observable universe were serious underestimates. If we extrapolate Webb's findings across the entire sky, always a risky proposition, but the best we can do, the number of galaxies in the observable universe might exceed 20 trillion. And remember, these are just the ones we can theoretically detect. Each new telescope generation reveals more galaxies we missed before. This exponential growth in our galactic sensors has profound implications. It means the universe is even more densely populated with galaxies than we thought. It means there are even more stars, more planets, more opportunities for life. It means the Milky Way is even more insignificant in the grand scheme than we realized. One galaxy among 20 trillion, and that's just in the observable universe. Beyond the observable, the universe we can never see. Here's where things get truly philosophical and a bit unsettling. The observable universe, that 93 billion light-year diameter sphere, isn't the entire universe. It's just the part from which light has had time to reach us. Beyond the cosmic horizon lies more universe. How much more? We don't know. We can't know through direct observation. The universe beyond our cosmic horizon is causally disconnected from us. No information can travel from there to here, because it would require traveling faster than light through space, which is impossible, or because the expansion of space is carrying those regions away faster than light can close the gap. Current observations strongly suggest the universe is flat, or very close to flat on large scales. A flat universe, in cosmological terms, is spatially infinite. It goes on forever in all directions. There's no edge, no boundary, no center. If you could somehow travel far enough, setting aside the expansion issue, you'd never reach an edge of space. You'd just keep going forever, passing through more space, more galaxies, more cosmic structures. This means that if the universe is truly infinite, and the evidence increasingly suggests it is, then everything that can happen does happen, somewhere. There are infinite galaxies, infinite stars, infinite planets, and given enough space and time, even the incredibly improbable becomes not just possible but inevitable, and in fact occurs infinitely many times. Somewhere in the infinite cosmos, there's another Milky Way, another Earth, another you, reading an article about the scale of the universe. In fact, if space is infinite, there are infinitely many copies of you. Some living lives nearly identical to yours, others diverging at various points. This isn't science fiction or philosophy. It's a logical consequence of an infinite, fairly uniform universe with quantum uncertainty. If space is infinite, and matter is distributed reasonably uniformly on large scales, which observations confirm, then any arrangement of matter that's physically possible will occur an infinite number of times. Your entire observable universe all 93 billion light-years of it, could be perfectly replicated somewhere beyond the cosmic horizon. In fact, if space is infinite, it is replicated infinitely many times. The Milky Way in this context isn't just a grain of dust. It's one of infinitely many grains of dust in an infinite cosmos. Dark matter and dark energy. The universe is mostly mysterious. As if the scale wasn't humbling enough, here's another perspective shift. We don't actually understand what most of the universe is made of. Ordinary matter, the stuff that makes up stars, planets, gas clouds, and every atom in your body, accounts for only about 5% of the total mass energy of the universe. Everything we can see, detect, and directly interact with is just 5% of what's out there. About 27% of the universe is dark matter, an invisible substance that doesn't emit, absorb, or reflect light. We know it exists because we can see its gravitational effects on galaxies and galaxy clusters. Galaxies rotate too fast to hold together based on the mass of their visible matter alone. There must be additional mass, a dark matter halo surrounding each galaxy, providing the extra gravity to keep it intact. The evidence for dark matter is overwhelming and comes from multiple independent sources. Galaxy rotation curves show that stars far from galactic centers are moving faster than they should if only visible matter were present. Gravitational lensing, the bending of light by massive objects, reveals invisible mass surrounding galaxy clusters. The cosmic microwave background shows patterns that require dark matter to explain, and computer simulations of structure formation in the universe only match observations when dark matter is included. Yet despite decades of searching, we've never directly detected a dark matter particle. We don't know what it's made of. Leading candidates include weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. But experiments designed to detect these particles have so far come up empty. Dark matter interacts gravitationally, but apparently through no other force, making it extraordinarily difficult to study. In November 2025, researchers using advanced simulations suggested that dark matter might be lighting up the heart of the Milky Way. A mysterious gamma-ray glow at our galactic center, first detected by NASA's Fermi Gamma-Ray Space Telescope, might be caused by dark matter particles colliding and annihilating each other. If confirmed, this would be the first direct detection of dark matter interactions, a major breakthrough in understanding this elusive substance. The simulations recreated the Milky Way's turbulent history, including massive collisions with smaller galaxies. These collisions, it turns out, dramatically reshape the distribution of dark matter in the galactic center. Previous models assumed dark matter would be distributed in a smooth, spherical halo. But the new simulations show that collisions create a much more complex, lumpy structure. This distorted distribution matches the observed pattern of gamma rays far better than earlier predictions. If dark matter is indeed producing these gamma rays, it provides crucial clues about dark matter's properties. The energy of the gamma rays suggests dark matter particles might have masses in a specific range, helping narrow the search for direct detection. It also confirms that dark matter particles can annihilate when they collide, converting their mass to energy, exactly what some theories predict. The remaining 68% of the universe is dark energy, an even more mysterious force causing the expansion of space to accelerate. Discovered in 1998 through observations of distant supernovae, dark energy seems to be a property of space itself, a cosmological constant pushing everything apart. The discovery of dark energy was completely unexpected and revolutionized cosmology. Before 1998, astronomers assumed the universe's expansion was slowing down due to gravity pulling everything back together. The question was whether there was enough matter to eventually halt the expansion and cause a big crunch, or whether the universe would expand forever, just at an ever-decreasing rate. Distant supernovae provided the answer, and it was neither option. The universe's expansion is actually speeding up. Galaxies are being pushed apart by a mysterious repulsive force that operates on the largest cosmic scales. The farther apart two regions of space are, the faster they're being pushed apart by dark energy. In 2025, data from the Dark Energy Spectroscopic Instrument, DESI, and the Euclid Space Telescope strongly suggested that dark energy might not be constant after all. It appears to have gotten weaker over the last few billion years. This was completely unexpected and throws our understanding of cosmic evolution into question. For 2 decades, cosmologists had assumed dark energy was the cosmological constant that Einstein proposed and later called his biggest blunder. A cosmological constant is literally constant. It has the same strength everywhere and at all times. But DESI's observations of millions of galaxies across cosmic history show subtle deviations from this assumption. The data hints that dark energy was stronger in the distant past and has been weakening over time. If dark energy is changing, then the ultimate fate of the universe is uncertain. Will expansion continue accelerating forever, eventually tearing apart galaxies, stars, and even atoms in a big rip? Will dark energy weaken enough for gravity to eventually halt expansion and reverse it in a big crunch? Will it decay entirely, perhaps transitioning to a different state? Or will the universe simply expand forever at an ever-slowing rate, ultimately becoming a cold, dark, dead expanse in a big freeze? We don't know. We can't know until we understand dark energy better. Some physicists speculate that dark energy might be the vacuum energy of space itself, a consequence of quantum fluctuations at the smallest scales. Others propose it's a new field permeating space, sometimes called quintessence. Still others suggest it might be a sign that Einstein's general relativity needs modification on cosmic scales. But what we do know is this: 95% of the universe is made of stuff we don't understand. We're like fish trying to understand the ocean, while only being able to perceive 5% of the water. Everything we can see and touch and directly measure, all the stars, planets, gas, dust, radiation, and matter, is just a tiny fraction of what's actually out there. The Milky Way is a grain of dust, but it's a grain of dust in an ocean that's mostly invisible and made of unknown materials. And that grain of dust is itself 95% composed of things we can't directly detect. The Milky Way's precarious future. Let's bring things back to our cosmic home and consider its future. The Milky Way isn't static, it's evolving, and in cosmically violent ways. As mentioned earlier, in about 4 to 5 billion years, the Milky Way will collide and merge with the Andromeda galaxy. This is inevitable. The two galaxies are locked in a gravitational embrace that will ultimately combine them into a single, massive elliptical galaxy. But there's another, more immediate potential threat that emerged from research in March 2025. Astronomers studying a massive spiral galaxy called 2MASXJ2345328-0449256, located about 1 billion light-years away, discovered it has colossal radio jets extending 6 million light-years across space. These jets are powered by an enormous supermassive black hole, billions of times the Sun's mass. This was shocking because such powerful jets are almost exclusively found in elliptical galaxies, not spirals like the Milky Way. The discovery suggests that spiral galaxies can survive, and even thrive, while hosting incredibly active supermassive black holes, producing devastating radio jets. The galaxy, which is 3 times the size of the Milky Way, also contains 10 times more dark matter than our galaxy. This massive dark matter halo apparently helps stabilize the galaxy's fast-spinning disk, despite the violent activity at its core. The supermassive black hole is actively feeding on material falling inward, and this accretion process powers jets that shoot out perpendicular to the galactic disk at relativistic speeds, close to the speed of light. If a spiral galaxy can not only survive but thrive under such extreme conditions, what does this mean for the future of galaxies like our own Milky Way? Asked Professor Joydeep Bagchi of Christ University, who led the study. Could our galaxy one day experience similar high-energy phenomena that will have serious consequences for the survival of precious life in it? The Milky Way's central black hole, Sagittarius A star, is currently fairly quiet. It's accreting material at a very slow rate, barely feeding at all by black hole standards. But black holes can transition between quiet and active states. A change in the accretion rate, perhaps triggered by a nearby star's orbit carrying it too close, could wake Sagittarius A star from its slumber. If such jets formed and happened to be pointed in our direction, the consequences would be catastrophic. The intense cosmic rays, X-rays, and gamma rays could strip away planetary atmospheres, cause mass extinctions, and make large regions of the galaxy uninhabitable for millions of years. Even if Earth itself weren't in the direct path of the jet, the increased radiation environment throughout the galaxy could have severe consequences for life. Astronomers believe the Milky Way likely had large-scale radio jets in the past. Evidence for this comes from the so-called Fermi bubbles, enormous structures of high-energy gas extending 25,000 light-years above and below the galactic centre. These bubbles might be remnants of a period of intense activity from Sagittarius A star, perhaps 6 to 9 million years ago, when the black hole was feeding vigorously and blowing powerful winds and jets into the surrounding space. The triggering event might have been a gas cloud or even another smaller black hole falling into Sagittarius A star. Whatever the cause, the resulting burst of energy inflated these massive bubbles, which persist to this day, even though the black hole has since quieted down. If such an event occurred again, and if jets formed pointing toward our region of the galaxy, life on Earth could face serious challenges. The likelihood of this happening soon is extremely low, and even if it did happen, the jets might point in a different direction entirely. We'd need to be extremely unlucky for them to aim directly at us. But it's a reminder that even our local cosmic environment is subject to violent, galaxy-scale events that could reshape the conditions for life. There's also the ongoing accretion of satellite galaxies to consider. The Sagittarius dwarf elliptical galaxy is currently passing through the Milky Way's disk. This transit sends ripples through our galaxy's stars and gas, potentially triggering bursts of star formation. In the densest star-forming regions, supernovae would be more frequent, increasing radiation levels throughout the region. These passages also perturb the Oort cloud, a vast spherical shell of comets surrounding our solar system. Gravitational disturbances can nudge some of these comets into orbits that bring them into the inner solar system, potentially increasing the frequency of comet impacts on Earth. Some mass extinction events in Earth's history might be linked to such perturbations. Over very long timescales, the cumulative effect of these galactic disturbances could influence the habitability of the Milky Way. Regions that are safe now might become dangerous zones of intense radiation and frequent supernovae. Conversely, regions that are currently dangerous might quiet down as star formation rates decrease with time. The Milky Way isn't a static home. It's a dynamic, evolving system where the conditions for life wax and wane over millions and billions of years. Cosmic perspective, small yet significant. So what does all this mean? How should we process the reality that our galaxy is just one among trillions, perhaps one among infinitely many, in a cosmos so vast it defies comprehension? One response is nihilism, concluding that nothing matters because we're so cosmically insignificant. If the Milky Way is just a grain of dust, and Earth is an atom within that grain, and each human is a subatomic particle within that atom, then what does it matter what we do? But this misses a crucial point. Significance isn't determined by size or by how much of the universe we occupy. It's determined by complexity, consciousness, and meaning. Every atom in your body was forged in the heart of a star. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created billions of years ago in stellar furnaces and supernova explosions, then scattered across space to eventually coalesce into planets and life. The carbon in your DNA, the nitrogen in your proteins, the phosphorus in your ATP molecules, these elements didn't exist in the immediate aftermath of the Big Bang. The early universe contained only hydrogen, helium, and traces of lithium. Every heavier element had to be cooked up inside stars over billions of years of nuclear fusion. When massive stars died in supernova explosions, they scattered these elements into space, seeding the interstellar medium with the raw materials for planets and life. You are literally made of stardust. We all are. The universe isn't just something we exist in, we are the universe, awake and aware of itself. And consciousness might be incredibly rare. Despite the trillions of galaxies and the countless planets they contain, we haven't yet found definitive evidence of life elsewhere. It's likely out there, The numbers suggest it must be, but it might be far more sparse than science fiction suggests. Consider what had to happen for life to arise on Earth. The planet needed to be in the habitable zone around a stable star, not too hot, not too cold. It needed enough mass to hold an atmosphere, but not so much that crushing gravity prevented complex chemistry. It needed plate tectonics to recycle carbon and regulate climate over geological timescales. It needed a large moon to stabilize its axial tilt and prevent chaotic climate variations. It needed Jupiter in the outer solar system to act as a gravitational shield, deflecting many comets and asteroids that might otherwise have bombarded Earth continuously. Even with all these conditions met, life took about 4 billion years to evolve from simple single-celled organisms to complex multicellular life. For 3 billion years, Earth was inhabited only by microbes. Animals appeared only in the last 600 million years, less than 15% of Earth's history. Intelligent, technologically advanced life arose only in the last fraction of a percent of Earth's existence. How many planets have all the right conditions? How many of those actually develop life? How many of those develop complex life? How many develop intelligence? And how long do intelligent civilizations last before destroying themselves or going extinct due to natural catastrophes? The Drake equation attempts to quantify these questions, estimating the number of communicative civilizations in the Milky Way. Depending on your assumptions, you get answers ranging from "we're alone in the galaxy" to "there are millions of alien civilizations out there." The truth is, we simply don't know. Earth might be one of a relative handful of places in the entire Milky Way where life evolved, and possibly the only place where it evolved into a species capable of understanding the cosmos and asking these questions. That makes us precious beyond measure, regardless of our physical size. Moreover, humans are the only species we know of that can appreciate the cosmic perspective. A bacterium doesn't contemplate infinity. A tree doesn't ponder its place in the universe. Even dolphins and chimpanzees, intelligent as they are, don't build telescopes or wonder about dark energy. We can contemplate infinity, marvel at the scale of existence, and find beauty in our insignificance. That capacity for wonder and understanding is itself remarkable. The Milky Way might be a grain of dust in the cosmic ocean, but within that grain of dust, life emerged. Consciousness arose. Music was composed, art was created, love was felt, questions were asked. Entire worlds of meaning and experience unfolded. Think about what that means. In most of the universe, the vast majority of space, nothing interesting happens. Gas clouds slowly collapse under gravity. Stars form, burn and die. Planets orbit their suns in endless mechanical repetition. Black holes consume matter, galaxies merge, all following the laws of physics with no awareness, no meaning, no purpose. But here, on this small planet, something extraordinary happened. Matter organized itself into living cells. Those cells learned to sense their environment, to respond, to reproduce. Over billions of years, life became more complex. Nervous systems evolved, brains developed, and eventually, consciousness emerged. The universe's matter becoming aware of itself. With consciousness came the ability to assign meaning, to value things, to care about outcomes. A universe without consciousness is a universe without meaning, just particles obeying physical laws. But a universe with consciousness is a universe where things can matter, where experiences can be good or bad, where beauty and truth and love can exist. From a cosmic perspective, Earth's biosphere, the thin layer of life covering our planet, is infinitesimally small. But from another perspective, it's the most complex thing we know of in the universe. The human brain, with its 86 billion neurons and trillions of connections, is more intricate than any galaxy. A single human mind contains more functional complexity than a supernova. The universe is vast and mostly empty. But complexity isn't about size, it's about information, organization, and interconnection. Life is complex, intelligence is complex, consciousness is complex, and by these measures, Earth and humanity represent some of the highest peaks of complexity in the known universe. Size isn't everything. In fact, when it comes to what really matters, consciousness, understanding, meaning, love, size might be irrelevant. Would you rather be a galaxy of dead matter or a living, thinking being? Would you rather span a billion light-years of empty space or experience a single moment of genuine insight or joy? The universe has given rise to consciousness, and consciousness has given rise to meaning. That's not nothing. That might be everything. The anthropic principle. Why we're here to ask. There's a philosophical concept called the anthropic principle that's worth considering in this context. In its simplest form, it notes that any observations we make about the universe are necessarily constrained by the fact that we exist to make them. We find ourselves in a universe that can support life because, by definition, we couldn't exist in a universe that couldn't support life. This might seem tautological, but it has profound implications. The universe's fundamental constants, the strength of gravity, the charge of an electron, the mass of the Higgs boson, appear to be finely tuned to allow for complex structures like atoms, molecules, stars, and ultimately life. Change any of these constants by a small amount, and you'd get a universe where stars couldn't form, or where carbon couldn't exist, or where chemistry couldn't produce complex molecules. Why are the constants tuned this way? One possibility is pure luck. We happen to exist in a universe with life-friendly constants. Another is designed by some external intelligence, though this raises more questions than it answers. A third possibility, suggested by some interpretations of cosmology and quantum mechanics, is that there are many universes, a multiverse, each with different constants. Most of these universes are sterile and lifeless, but in the rare universes where the constants happen to allow for life, observers eventually arise to wonder about it all. In this view, the Milky Way isn't just one galaxy among trillions in our universe. Our universe might be one among countless others in a vast multiverse, and most of those universes are empty and dead, never observed by anyone because there's no one to do the observing. We exist in this particular universe because this universe is one of the rare ones capable of producing observers. It's not special because of us, rather, we're here because it's special. DESI's cosmic map, seeing further than ever before. The Dark Energy Spectroscopic Instrument, DESI, which released its data release 1 in March 2025, has created the largest 3D map of the universe ever assembled. Over its first year of operations, DESI catalogued the positions and distances of more than 4 million stars, 13.1 million galaxies, and 1.6 million quasars, the most distant objects we can observe. This 270 terabyte dataset represents an unprecedented view of cosmic structure, spanning from the present day back to 11 billion years ago, covering most of cosmic history since the Big Bang. What DESI's map reveals is a universe of incredible structure and complexity. Galaxies aren't randomly distributed. They're organized into an intricate cosmic web of filaments and sheets surrounding vast voids. This structure emerged from tiny quantum fluctuations in the very early universe, amplified by cosmic inflation, and then slowly shaped by gravity over billions of years. DESI's map also provided hints that our standard model of cosmology, the lambda CDM model that's been so successful, might need revision. The data suggests dark energy is behaving differently than expected, evolving over cosmic time rather than remaining constant. DR1 already gave the DESI collaboration hints that we might need to rethink our standard model of cosmology, said Stephen Bailey, who leads data management for DESI at Lawrence Berkeley National Laboratory. The implications are profound. If dark energy is changing, it means the universe's future is less certain than we thought. The expansion rate might not continue accelerating forever. The universe's ultimate fate, which we thought was settled, is back in question. But perhaps the most important contribution of DESI's map is simply showing us the universe in unprecedented detail and scale. It reveals patterns, structures, and evolution that were previously invisible. It makes concrete what was once abstract. The Milky Way appears in DESI's map as just one of millions of data points, one galaxy among countless others. But the map itself exists only because conscious beings in that one galaxy built the instrument and asked the questions. The cosmos is examining itself through us. Gaia's 11-year legacy, mapping our home. While DESI mapped the distant universe, the European Space Agency's Gaia mission spent over 11 years mapping our home galaxy in unprecedented detail. The spacecraft completed its survey in January 2025, having observed nearly 2 billion stars, about 1% of the Milky Way's total stellar population. Gaia measured not just the positions of these stars, but their motions, brightnesses, colors, and temperatures. This allowed astronomers to create a three-dimensional dynamic map of the galaxy, showing not just where stars are, but how they're moving and how they'll move in the future. The discoveries from Gaia have revolutionized our understanding of the Milky Way. The mission revealed the galaxy's warped, wobbling shape, a giant wave rippling outward from the center, evidence of multiple past collisions with smaller galaxies, streams of stars from dwarf galaxies being torn apart by the Milky Way's gravity, the detailed structure of the galactic disk and halo, tens of thousands of binary stars, variable stars, and other exotic objects, precise distances to nearby galaxies, recalibrating the cosmic distance scale. Perhaps most poignantly, Gaia traced the motions of nearby stars into the future, showing how they'll move across the sky over the next 400,000 years. The familiar constellations we see today, Orion, the Big Dipper, the Southern Cross, will slowly change shape as their component stars drift in different directions. Even our sky is temporary. Gaia also helped establish the Milky Way's place in the cosmic web by precisely measuring distances to nearby galaxies and tracing the gravitational influences that shape galactic motions. We now know the Milky Way is being pulled toward the Virgo cluster as part of larger-scale flows within the Laniakea supercluster. All of this painstaking work serves a simple but profound purpose: understanding our cosmic home. The Milky Way might be just one grain among trillions, but it's our grain. And Gaia has shown us what an intricate, dynamic, beautiful grain it is.
The search for meaning in a vast universe. As we contemplate the scale of existence, from our planet to our galaxy, to the hundreds of billions of galaxies in the observable universe, and potentially infinitely more beyond, we're forced to reckon with questions of meaning and purpose. If the universe is so vast, and we're so small, does anything we do matter? If there are infinite copies of Earth somewhere in an infinite cosmos, does our particular Earth's fate matter? These are ultimately philosophical rather than scientific questions, but science can inform how we think about them. First, consider that consciousness and intelligence are probably the rarest and most valuable things in the universe. For all its vastness, most of the cosmos is simple: hydrogen gas, radiation, space-time. The complex chemistry required for life is rare, and the evolution of intelligence is probably even rarer. We might be one of only a handful of civilizations in the entire Milky Way. In the observable universe, there might be millions of worlds with intelligent life, but that's millions among trillions of galaxies. Most galaxies might be entirely lifeless. If consciousness is rare, then it's precious. Every mind is valuable. Every moment of awareness, understanding, love, creativity, or wonder is a victory against the entropy and indifference of the universe. Second, meaning isn't something you find in the cosmos, it's something you create. The universe doesn't care about human concerns, but that's not a flaw, it's a feature. It means we're free to create our own values, to decide what matters, to build meaning from the ground up. The fact that we're cosmically insignificant doesn't make our lives meaningless. It makes our creation of meaning all the more remarkable. Against all odds, in a universe of mostly empty space and dead matter, conscious beings arose who can love, create, understand, and care. That's not nothing. That might be the most significant thing in the entire cosmos. Third, we're connected to everything. The atoms in your body were forged in stellar furnaces. The energy powering your cells comes ultimately from nuclear fusion in the sun. The complex chemistry of life exploits quantum mechanical effects at the molecular level. You are made of space-time, built from quarks and electrons governed by the same laws that shape galaxies. You're not separate from the universe looking out at it. You're part of the universe looking at itself. Every human thought, every moment of consciousness, is the universe becoming self-aware. When you contemplate the scale of the cosmos, you're not diminished by the comparison. You're part of the cosmic story. A small part, yes, but an integral one. Looking forward, the future of cosmic discovery. The revelations about cosmic scale from JWST, DESI, Gaia, and other instruments are just the beginning. Several next-generation facilities will push our view even further. The Vera C. Rubin Observatory, beginning operations soon, will map billions of galaxies and track how they change over time. The Nancy Grace Roman Space Telescope, launching in 2027, will conduct massive surveys to better understand dark energy and search for exoplanets. Ground-based extremely large telescopes, the Extremely Large Telescope in Chile, the 30-meter telescope, the Giant Magellan Telescope, will have collecting areas larger than anything that came before, allowing them to study the faintest, most distant galaxies in unprecedented detail. Future space missions might include gravitational wave detectors like LISA that will observe the ripples in space-time from merging supermassive black holes across the entire universe. Advanced neutrino detectors might reveal cosmic events invisible to light-based astronomy. As our instruments improve, we'll continue discovering that the universe is larger, more complex, and more surprising than we thought. The pattern has held for centuries. Every advance in technology reveals more. There's no reason to think we're approaching the end of that trend. And perhaps, one day, we'll detect signals from another civilization, a radio transmission, a laser beacon, an anomaly in stellar spectra that can only be explained by advanced technology. If that happens, the Milky Way's status as just another galaxy might change. Our grain of dust might turn out to be special after all, or at least one of a community of special places where intelligence arose. Until then, we're alone with our cosmic perspective, simultaneously humbled and ennobled by our place in the infinite. The view from our grain of dust. Let's return to Earth for a moment. This planet, this pale blue dot suspended in a sunbeam, as Carl Sagan called it, is home to all human experience. Every joy and suffering, every triumph and tragedy, every act of kindness and cruelty, every dream and fear, all of it happened here on this small world. From space, Earth is nearly invisible. The most powerful telescope couldn't resolve individual humans from even the distance of the Moon. From Pluto, Earth is just a point of light. From the nearest star, Earth is undetectable with current technology. Our entire planet fades into the glare of the Sun. The Milky Way is invisible from outside itself. We can't take a photo of our galaxy from an external vantage point because we can't leave it. Every image you've seen of the Milky Way is either taken from within, showing the band of light across our night sky, or an artistic illustration based on observations of similar galaxies. From another galaxy, the Milky Way might be detectable with advanced instruments, but individual stars would be impossible to resolve. The Sun would be lost among hundreds of billions of others, and from beyond the local group, the Milky Way becomes just one of countless galaxies in a vast cosmic tapestry. Zooming out further, even galaxy clusters become mere points in the cosmic web. Eventually, at the largest scales, even superclusters blur together into the overall uniformity of the cosmos. From the ultimate cosmic perspective, Earth is less than a pixel, the Sun is invisible, and the Milky Way is one unremarkable galaxy among trillions. And yet, despite all this cosmic insignificance, or perhaps because of it, the fact of our existence is remarkable. Against staggering odds, in a universe that's mostly empty and dead, complex chemistry arose. Life emerged, consciousness evolved, and that consciousness developed the capacity to understand its place in the cosmos, to grasp the scale of existence, to ask these very questions. We're the universe contemplating itself. We're how matter comes to know matter, how space and time become self-aware. That's not diminished by our small size. If anything, it's more remarkable because of it. The Milky Way might be just a grain of dust in the infinite cosmos, but within that grain of dust is everything that matters to us: our history, our future, our hopes and dreams, every story ever told and every song ever sung, all of art, science, philosophy and culture. If meaning exists anywhere in the universe, it exists here, within this grain of dust, within the minds of conscious beings who can appreciate the infinite while cherishing the finite. The universe is incomprehensibly vast. We are incomprehensibly small, and somehow, miraculously, we're here to notice. Thank you so much for joining me on this journey through cosmic scale. from our home galaxy to the infinite reaches of space beyond. If you enjoyed exploring our place in the universe and want to learn more about the latest discoveries in astronomy and cosmology, please subscribe to stay updated. There's so much more to discover about the cosmos we call home, and each new finding makes our grain of dust seem both smaller and more precious. Don't forget to hit that subscribe button so you won't miss future explorations of the wonders of the universe. Until next time, keep looking up, and remember, you're made of star stuff.